Alright, pre-calc, back with the second video for 9-1. This is day 2. Um, this is really nice. It's another day with just one page of notes. There's not really too much being covered in content. Um, I think the homework exercises might be a little bit difficult because not only do you have to write out the terms of a sequence, when they tell you what the first term is and what the rule is or something like that, but in your homework, it's going to tell you to look at some sequences and then tell them what the rule is. And that is far more difficult to be able to just look at a list of numbers and recognize what the pattern is. So I think the content is going to be relatively easy for what we're covering, but the problems might be a little bit challenging. Day 2 covers summations. So it wants us to start out by reading the top of page 644 up until example 7. The top box will give us the definition of summation notation. So I'm going to run over to our book here. It says there's a convenient notation for the sum of the terms of a finite sequence. It is called summation notation or sigma notation. So you might hear me refer to this as sigma notation because it involves the use of the uppercase Greek letter sigma, written as, well, you can see what the symbol they use there. The sum of the first n terms of a sequence is represented by this symbol right here. So it's the uppercase sigma with, on the bottom it says I equals 1, on the top it says n, and then a sub I on the right. What that bottom term tells you is at what term you're starting. So you can look on the right side and it says you're starting with the first term. A sub 1 is your first thing. And so that's why you have I equals 1 in the bottom. The n on top tells you where you stop. So we can see that this is the finite sum from A sub 1 all the way up to A sub n. So the nth term is where we stop. And the A sub I out front just tells us what we're summing. We are summing the A sub i's from I equals 1 all the way up to n. So yeah, I is called the index of summation, n is the upper limit of summation, and 1 is the lower limit of summation. So let's just copy that into our book. It wants us to say, okay, what does this notation mean? I say, okay, this is the sum from I equals 1 to n of A sub I. So I'm going to start with A sub 1. I'm going to add A sub 2, add A sub 3, add all the way up to, A sub n minus 1, and then all the way up to A sub n. That's all this notation means, a sum of the first n terms. Okay. It wants us to read carefully through example 7, then try exercise 85. So I'm going to read through example 7. I want to make clear if at any point in this video you feel like you understand things, feel free to skip ahead. YouTube has a nice feature where you can speed this up if you feel like I'm talking too slowly or something. Or likewise, you can slow things down. So, example 7 is just showing us how to do sums of a few different sequences. So, like the first one, it's the sum from I equals 1 to 5 of 3i. So the rule for the sequence there is 3i. So when they're finding the first 5 terms, the first term is 3 times 1, the second term is 3 times 2, the third term is 3 times 3, fourth and fifth, so on. And you can see how, again, they're just adding here. It's no big deal. The purpose of this example is just to get you used to the notation. It's the same thing for the next sequence, except for this one, they're not starting at the first term, they're starting at the third term. So it's from k equals 3 to k equals 6. So they have 1 plus 3 squared, 1 plus 4 squared, 1 plus 5 squared, and 1 plus 6 squared. Here, again, the rule is just different. On the last one, we had, the rule was 3i for every term of the sequence. If it was the fourth term, you plug in 4 for I. On this one, the rule is 1 plus k squared. So if you want to find the third term of the sequence, you plug in 3 for k. And again, you can see that instead of using I, they use k. Your choice of variable here doesn't matter. You could use A or B or C, whatever. They use I and K because I and K are just kind of, there's just tradition to use those. Okay, if you want to read through the rest of that example, that's fine. I'm going to move on to exercise 85. Again, the purpose of this is just to get you comfortable with some of the notation that's being used. So let's take a peek at 85. It wants us to find the sum. So the sum from I equals 1 to 5 of this thing, 2i plus 1. So the sum from 1 to 5 of 2i plus 1. Let's see what we can do. Okay, and then it's simply a matter of figuring out what these 5 sequence terms are and adding them together. The first term, if you just plug in 1, is 2 times 1 plus 1. The second term is 2 times 2 plus 1. So maybe I'll separate these with parentheses so you can see the clear distinction. So it's 2 times 2 plus 1. The third term is 2 times 3 plus 1. Again, I hope if you did yesterday's assignment, I hope like finding out what these individual sequence terms are is pretty intuitive to you by now. If you haven't done the exercises from 8.1, I would stop the video right now and do those. So now we just need to calculate all this. So this first term, 2 plus 1 is 3, 4 plus 1 is 5, 6 plus 1 is 7, 8 plus 1 is 9, 10 plus 1 is 11. So it's 3 plus 5 is 8, 8 plus 7 is 15, 15 plus 9 is 24, 24 plus 11 is, I believe our answer should be 35 here. Guess you can double check me on that. I'm pretty tired. I might not be doing my arithmetic right, but yeah, I mean, when you do these sum problems, I mean, for the most part, you should just come up with numbers. I mean, you're just summing lists of numbers. Okay. On the top of page 645, there is a table listing the properties of sums. List these properties below. So I'm actually going to really quickly erase this because I got to scroll down again, and for whatever reason, it won't let me scroll with the writing. What the heck? Okay, I'm going to go to 645. It's going to give us the 4 properties of sums, of summations. It's important to know your properties so you can know what kind of things you can do with sums. Just makes things a lot easier for you. Okay, here are our properties. So the first one is that the sum of C, where C is a constant, so just like the sum of any number from 1 to n, is just equal to C times n. Basically, all that first property is saying is that if you take a number and add it to itself n times, well, you just get that number times n. That's really all it's saying. So the first one is like the sum of C from I equals 1 to n is equal to C times n. And that makes intuitive sense. It's maybe the only thing here that's weird is the notation. Let's look at the second property. It's the sum of C times some function here. Again, we don't really know what a sub I is in this case. So they're saying if you have the sum of C times a sub I from the first term to the nth term, they're saying here is that you can just like factor this constant out. So I think maybe like an example there is helpful. So like if you were summing 3i from I equals 1 to n, you could just factor that 3 out before you even start. And you could just sum I from I to n and then multiply the result by 3. So I just put an example of that property in my notebook. You can do what you want. I think it's more intuitive that way, maybe to just have the example. The third property is saying if you take the sum from 1 to n of a sequence a sub I plus another sequence b sub I, what this property is saying is you can just split them up and treat them separately. So in this case, maybe I'll just do another example. I think maybe that's the most intuitive. So for 3, they're saying, suppose you have the sum from I equals 1 to n of 3i minus 2i. Well, you could just split those up into 2 separate sums. Or actually, I'm going to say 3i squared minus 2i, because I think otherwise you can just simplify. You could split these up into 2 separate sums. So you could have like 3i squared minus the sum of 2i. So, I mean, this can be nice when you have like a really complicated rule right here. It can be nice to like split it up into separate sums. That's all that rule says. Okay, the last rule, the last rule is really just like the first. In the first one, it says if you have the sum of 2 distinct sequences, you can sum them separately. The fourth property here just says if you have a difference of 2 sequences, you can sum their difference separately. That's all it's saying. I'm not even going to write that one down because I basically ended up writing down property 4 for my example for property 3. I think it's pretty intuitive. Okay, so those are just properties of sums. Now the second thing we're moving on to in today's notes are series. So it wants us to read the definition of series in the middle of page 645 and then determine what the difference is between a partial sum and series. So I'm going to go to page 645 here and I'm going to read the definition of the series. Many applications involve the sum of the terms of a finite or infinite sequence. So the difference here is between a finite or infinite sequence. Such a sum is called a series. So let's look down here at the definition. Consider the infinite sequence, a sub 1, a sub 2, a sub 3, all the way off to infinity. The sum of the first n terms of the sequence is called a finite series or the nth partial sum of the sequence. So I'm going to be clear, if you're summing the first n terms, we call that a finite series or we call it the nth partial sum. Remember that vocab because you'll be asked about it in your homework. And that's just denoted by, just like we did in the earlier examples. It's the sum from I equals 1 to n of our sequence. Again, that's just called an nth partial sum. The new thing here, a series, is what you see in number 2. The sum of all the terms of the infinite sequence is called an infinite series and is denoted by this, you can see below. So a sub 1 plus a sub 2 plus a sub 3, all the way up to an infinity, it's denoted exactly the same way, except we say, okay, you start at I equals 1, but you go to infinity. So instead of writing n up here on the top of our sigma, you write an infinity symbol instead. And that's the difference between a partial sum and a series. A series is the infinite sum. So our notes ask us to determine what is the difference between a partial sum and a series. Well, a series is an infinite sum. Or I could say a series is the sum of an infinite sequence. Now, like for me, when I first learned about series and sequences, I thought, well, what point is there to talking about the sum of an infinite series? Because doesn't the fact that it's infinite mean that the sum is always going to be infinite? And we're going to see that that's not the case. There are many infinite sequences that actually sum to a finite number. And it's kind of a weird thing. We'll talk about that more in like section 9.3. But yeah, the difference between a partial sum and a series is that a series is infinite. It's the sum of an infinite sequence. Okay. This wants us to read through example 8, then try exercise 113. So I'm going to find example 8. And it says it wants us to find the sum of a series. So we're finding the sum of an infinite sequence. So in the first part of this example, they're finding the third partial sum, and in B they're just finding the sum. So that means they're finding the sum of the entire series, the whole infinite series. So for the third partial sum, you can see that they're just summing from 1 to 3. That's what the third partial sum means. So it's like 3/10 plus 3 over 10 squared plus 3 over 10 cubed. And they get an answer. You can read through that. The second part is more interesting because they're doing an infinite sum, a sum of an infinite amount of numbers. And so the first term is 3/10 or 0.3. The second term is 3 over 10 squared or 0.03. The third term is 3 over 10 cubed, and that's 0.003. The fourth term is 3 over 10 to the fourth, and so on. And you can kind of see this decimal pattern emerging here. You get 0.3, and then you get 0.03, and then you get 0.003. And they were able to combine that infinite sequence. They could see the pattern here, that the sum of all these things is actually just 0.3, 3, 3, 3, 3, 3, 3, and so on. And you know, if you can't see that, you know, pause the video and take a minute to look at why that's true. Well, 0.333 repeating, that's just equal to 1/3. So this is an instance where we have the sum of an infinite sequence, or we call it the sum of the series, and it actually turns out to be a number, 1/3. And that's kind of interesting, how you could add infinitely many numbers together and still get a finite sum. Okay, now we need to look at exercise 113. So scroll down to our exercises, find 113. Okay, so in exercises 113 through 116, find the indicated partial sum of the series. So we're only finding partial sums here, not total sums. So we have this series, I equals 1, and it wants us to find the fourth partial sum. So I'm going to write that right away, just the fourth partial sum. So from I equals 1 to 4 of, I need to go back and figure out what the series is, 5 times 1/2 to the I. So 5 times 1/2 to the I. Okay, and here is the point where our properties of sums come in really, really nicely, because we know from our properties of sums that we can just take that 5 out front. That's really convenient, so we don't have to worry about that until the end. Now I'm just finding the fourth partial sum. That's the sum of the first 4 terms. So I'll leave that 5 out front. The first term is just 1/2 to the first power. So 1/2 to the first power. The second term is 1/2 to the second power. 1/2 to the second. Third term, 1/2 to the third. You can see the pattern here, 1/2 to the fourth. It's our fourth term. This is the fourth partial sum. Okay, 1/2 to the first power, 1/2. 1/2 to the second power is 1/4. 1/2 to the third power is 1/8. And 1/2 to the fourth power is 1/16. We need to add all these together, and to do that you need a common denominator. I'll say, you know, if you want to plug this into your calculator, I don't have a calculator, so I got to figure this out. 1/2, that's like 8/16. 1/4, that's like 4/16. 1/8, that's like 2/16. So 1 plus 2 plus 4, 7 plus 8. So that's going to be 15/16 inside the parentheses there. So 5 times 15/16. And if you multiplied that out, you would get 75 over 16. So that is the fourth partial sum of the sequence they asked you to find. So let us move on to applications. Lots of applications of sequences and series. They're really important for, they're really important in all sorts of fields. But I mean, this is a pre-calculus course, so there will definitely be some calculus applications, and we'll see those as we go forward. Let me just erase all this real quick. Okay, perfect. Okay, so it says page 646 shows us a couple of applications of sequences and series. Read through example 9 to see how we can apply sequences to compound interest. Then try exercise 121. Okay, so I need to read through example 9. Yeah, compound interest is a very, very common application of sequences and series. So what they're telling you here in example 9 is that a deposit of $5,000 is made in an account that earns 3% interest compounded quarterly. So compounded quarterly, that means they compound it 4 times a year. The balance in the account after n quarters is given by a sub n is equal to 5,000 times 1 plus 0.03 over 4 to the nth power. Basically here, you don't need to worry about, I guess, how they got this. You can think about it, or you can come in and ask us if you want to know why this formula is true. But they're basically giving you a sequence that tells you the amount of money in your account after n quarters. And a quarter, is every 3 months. So this sequence will just tell you how much money you have. So first thing they do is write the first 3 terms of the sequence. So again, that's just as simple as plugging in 0 to the formula, plugging in 1, plugging in 2, and computing that. So you can kind of see that, in the 0th quarter, the money hasn't changed at all. No time has passed. By the first quarter, after the first quarter's passed, we've made $37.50. And you can see how that continues. In B, they find the balance in the account after 10 years. And 10 years, since there's 4 quarters in a year, is like the same thing as finding the 40th term of the sequence. So you can see that there in B, that after 10 years, our initial investment of $5,000 has grown to $6,741.74. So again, they're just giving you a sequence here, and that sequence corresponds to how compound interest works. And this is really how compound interest works. So it wants us to try exercise 121 for ourselves. And I believe exercise 121 is, just another compound interest activity. So it says here, you deposit $25,000 in an account that earns 7% interest compounded monthly. So instead of being compounded quarterly, we're compounding monthly. The balance in the account after n months is given by this sequence. And if you want to learn a little bit more about how compound interest works, you can kind of compare this initial formula to the one in the last example and kind of note the differences. Compounding things monthly is different than compounding things quarterly. You'll earn different amounts of money. So it's giving us this sequence. It says this sequence tells us how much money we have with compound interest. Write the first 6 terms of the sequence. So I'm actually going to copy down this formula into our notebook here. So a sub n is equal to, I believe I deposited 25,000. Yeah, okay, I deposited 25,000. 25,000. That's 1. It's 1 plus 0.07 divided by 12 to the nth power. So that's our formula. Find the first 6 terms of the sequence. This is a matter of number crunching. So 8, 1, I mean, again, it's just a sequence. You just plug in 1 for n. So it's 1 plus 0.07 over 12 to the first power. You can plug that in your calculator again. I don't have a calculator with me at the moment. So a sub 2, so after 2 months, our interest would be, again, 25,000. It's our initial amount, plus 0.07 divided by 12 to the second power. So this first term here, it's once we compute that tells us how much interest and like how much our money is now worth after 1 month. This tells us how much money we have after 2 months. So, I mean, I'll let you compute the next 6 terms on your own. I think that's relatively straightforward. In B, it wants us to find the balance in the account after 5 years. And what they're telling you here is that 5 years, since every year has 12 months, that's like the 60th term of our sequence, because our sequence is in terms of months. So after 5 years, that's the same thing as our 60th month. So that's 25,000 times 1 plus 0.07 over 12 to the 60th power. And again, punch this into your calculator. The nice thing about the sequence we have here is, I don't know if you remember from day 1, we talked about recursively defined sequences. In a recursively defined sequence, we would have had to know all 59 terms that came before this term to figure out what was going to happen on the 60th term or in the 60th month. It's really nice that the compound interest sequence isn't that, so we can easily compute how much money we're going to have after 5 years. Okay, so C says, is the balance after 10 years twice the balance after 5 years? And then it wants us to explain. So if we want to figure out if the balance after 10 years is twice as much as the balance after 5 years, we need to actually figure out what is the balance after 10 years. So if you're good with your mental math here, you know that 10 years is like 120 months. So if we want to figure out the balance after 10 years, we just figure out what a sub 120 is in our sequence. Okay, I feel like at this point I do need to find a calculator because the rest of the activity won't make sense without it. So I'm going to really quickly compute these. Sorry if you've already got them. So after 5 years, I have that we have $35,440.63. You can fact check me on that, but I hope that's right. After 10 years, we would get $50,241.53. So we've computed how much money we have after 5 years. We've computed how much money we have after 10 years. And it's very obvious that 50,000 is not double of 35,000. So after twice the time, our money didn't double. What it's asking us to do in part C is it wants you to explain this. So like what you know about like compound interest and things like that, why is it that after 10 years, which is twice the amount of 5 years, why hasn't our money doubled? And I want you to think about that and try to explain that on your own. Try and figure out, why wouldn't sequences work like that? So think about that, fill that out. If you have questions, bring them to class tomorrow. Yeah, that is the end of this section. Again, if this was too long for you, feel free to speed up the videos. If this was too short, feel free to slow them down and make sense of the reading on your own. I don't want you to use this as an excuse to not read. I want you to be doing the reading and filling out the notes. So I hope hope you have a good weekend or whenever you're watching this, and we will see you in class.